Can you hear me? Okay, good.
Co? Rudy? Dopadł kot. Jego własny.
I used to work for the Akka team, but I converted to the Typesafe console team. But I'm going to give you a presentation about Akka, and after that, some business cases, and finish off with the Typesafe console. How many of you have heard of Akka before? 30%? Okay, good.
Ja pisać w Javie, ale kiedyś to pracować w Java.
Jonas Bonnier, who's the founder of Akka, he likes to do hiking, and he climbed the summit there and decided that he was going to use Akka as the name of the framework. So what is Akka? Everything I'm going to talk about today is Akka works from a Java environment or a Scala environment. So I'm going to present this in Scala, of course, this being a Scala conference. But you can use it from Java as easily if you want to. Which basically means that you can use it in your existing Java environment. Most of you guys are into Java, I guess. How many are doing Scala full-time or working with Scala, getting paid by doing Scala? Okay, 5 persons. And how many are doing Java? Sort of the rest, I guess. Or any other languages, Scala, Java? Okay, I guess Ruby, Python, PHP, Pascal. Airline, okay, cool. Yeah. So you'll recognize some topics from here. Right. Before I start off, I wanted to show you a couple of production users that have Akka in production. You might know some of them, like Amazon.com. A lot of banks and financial institutions are turning to Akka for scalability. HSBC, UBS, media companies, but also a lot of small startup companies like Box, for example, which is into media. It's online collaboration between TV. Right. So one of the leading themes in Akka and the Akka team has always been that you should be able to scale up and out. So we have people running Akka on their Android phones for fun, not for business, I guess. So it's possible to run Akka on your Android phone. It's also possible to run it on a Zoom machine if you want to. So that's sort of scaling up. And then we have scaling out. So you can run it, of course, on your local machine. You can also run it in the cluster. And the cool thing about it is that you don't have to change anything of your production or your code. It's sort of a configuration that you put next to your code that decides how to run Akka. So one of the leading themes has always been to manage system overload. You should be able to, as I said, program one way, and then you can deploy to what environment you're going to use. I mean, you might not know beforehand how successful your application will be, right? Hopefully it will become a new Facebook, but not all the time it is. And these guys decided to take this truck because it said turbo on top of it, I guess. Tried to take it over the mountain, didn't work out that well. So what we want you to do is program at a higher level. You should not have to think about terms of shared state or state visibility, threads, locks, concurrent collections, and so on. This is something that is really tricky to do right. Java developers have been protected by using an application server, but if you're doing hardcore thread programming in Java, you know that it's difficult to do it right, and most of the time you do it wrong. So instead, we want you to think of your programming as a flow in the system, and I'm going to explain further on what I mean by that. And by doing this, you should get high utilization of your CPU, low latency, high throughput, and so on, for free by just using the model. So you don't have to learn all these tricky things about how thread works in Java in order to utilize what you have in hardware. And the reason we know this and can be so certain about that this is a valid statement is that it's been proven before by the airline guys, for example. So as I said, Akka is distributable by design, which means that so one of the core concepts in Akka is something called an actor. I will explain later on what an actor is. But when you develop an actor, you don't know if it's going to be run on your local machine or if it's going to run in a distributed environment. The development model is exactly the same. So then you get scaling up and out for free. And this basically means that it's perfect for it's the perfect fabric for the cloud. You don't have to think about things like this. When you program, just use the actor model when you program and you will get this. Right. So what are the business benefits of using Akka? Okay. So lower the development costs, more functionality and scalability with less lines of code. And I mean, especially if you're going to use Akka from a Scala environment, it's so little code you can't believe it. Java is a little bit more because we have to do some things there, but still it's little code to write. It's faster to build the system, and it's easier to understand the system, especially in comparison to if you're doing thread programming, where it's really tricky to reason about what's going on in the system. Here you always know, sort of, you have the model, and you can reason around the model. It's quite an easy model. Therefore, it's also easier to maintain the system and evolve the system. And then finally, we believe that this will produce less bugs. So there are also lower operations costs by using this. It's open source, so you can use it for free. It's lower cost on the hardware side because we're utilizing so much of the existing hardware, so you don't have to buy new machines in order to scale up. And a really important thing here is that we the way the model produces safety around what you're doing, so therefore it's less downtime. I will show you later how that works. Right. So this basically enables you to write your program, as I said before, in one way and target different environments. So you can write it to just be a normal batch analysis system. And then when it becomes this Facebook hit, you can also reuse the same code basically, write some new configuration files and deploy into the cloud and handle much more requests per second if you want to. Right. So, okay, so that was sort of the business side of things. Now I'm going to go into the technical stuff to show you how we can achieve this. I promised a lot, right? So now I need to live up to it. So how can we do all this? Let's use actors. How many of you have heard of actors before? Okay, a third, I guess. Okay, so Akka's unit of code organization is called an actor. And actors, the way actors are, they help you to create a concurrent, scalable, and fault-tolerant applications. Actor is also a model for organizing your code. And it separates sort of the logic, or the business logic. You can write business logic cleanly inside your code and then do the other stuff on the side. And actors have actually been around since 1973. Carl Hewitt coined the term actor in 1973. And it's been used in telecom systems with 9 nines uptime. And here's the pop quiz. How many, what per year, what's the downtime if you have 9 nines uptime? Do anyone know?
5 minutes by 10 years.
Couple of seconds. No, 5 minutes.
For 10
Okay, we have a
years.
couple of seconds, we have 5 minutes.
For 10 years.
5 milliseconds is closer, it's 31.5 milliseconds downtime per year. How many of you who've written systems in production have produced 31.5 milliseconds downtime per year? Yeah. Erlang, right?
No.
No? Okay. Okay, that's really good. So there are systems, telecom systems, written in Erlang that have actually 99s and the C program. I would say that's probably the only C program that has 99 sometimes. Yeah. So what can we use actors for then, if they're so good? Well, we can use it as an alternative to a thread, or it could just be an object instance or a component, a callback or a listener, of course, a singleton or a service, a router, a load balancer or a pool, an out-of-process service, or a finite state machine if you want to. And the cool thing is, regardless of how we decide to use it, it's the same model. So we don't have to change anything. We just have to adhere to these rules that we set in that framework, and then you can decide how you want to apply it. So the actor model, in Carl Lewitt's definition, is the fundamental unit of computation that embodies processing, storage, and communication. And the three axioms are: when an actor receives a message, it can create new actors, it can send messages to actors it knows, and it can designate how to handle the next message it receives. So it's sort of behavior and state in one component. In Erlang, you can only communicate with your own children, or the actors you've created as an actor. In Akka, that's not true. You can also decide to communicate with other actors, because we're using sort of an address. And in that address space, you can call whatever actor you want to. Okay, so now I'm going to show you some code. It's all going to be in Scala. But as I said before, you can as easily do it from a Java environment. We have 100% compatibility between the two the Scala side and the Java side, Java API and Scala API. So I'm going to start off with showing you how to define an actor, and then create, send, become, and supervise. Right. So let's start off with defining the actor. First of all, we created a case class here. And case classes are great, by the way, in Scala. This one is really easy. It's just carrying a string, who, and the class is called greeting. The next step is to actually define the actor class, and we do that by extending actor. And the with actor logging here is a mixin of a trait that enables us to write log.info. We get sort of the logging framework into the code directly there. So that's the only thing it does. Yeah. And then we define the actor's behavior. And we do this, the only thing you have to do when you actually extend an actor is to define this method called receive. And in receive, you have pattern matching. So we're using pattern matching here. So I'm expecting something called a class, I'm expecting a class greeting with a message called who here, or yeah. And then I can just print, sort of extract the who into the log info there, you see where we append it to. So that's all you have to do. Define, extend actor, and define the receive method. You can pattern match on anything here. It doesn't have to be classes. It can be strings, numbers, whatever.
Maybe you will mention about that, about what about the loop and react idiom in Scala when you have an actor. You can put a loop and react. Know it?
No, I don't know what you mean there.
This is something which is used to
The remote actors.
old.
The old, oh, okay, in Scala actors. Okay, I haven't done Scala actors, so I don't know, sorry. And Scala actors are deprecated, they're being replaced with Akka in 2.10, so.
The receive is the React method and the loop is implicitly by actor.
Okay.
Okay, yeah, good. So this is all we have to do to define the actor. Right, so the next step would then be to create it. And it's extremely lightweight to create actors. We've done some tests, and in our environment we can get approximately 2.7 million per gigabyte RAM if you want to. And as I said before, it's very strong encapsulation because an actor encapsulates state and behavior. And it also has a message queue on the side. And this means that you never know what state an actor is in. The only way you can communicate with it is by sending messages to it. And this can be weird when you're, as a Java developer, you're normally a little concerned about that if you can't control things. But Akka is totally asynchronous, so there's no way of knowing what's going on the other side. The only way you can send a message to an actor and then have it tell you back what's going on with it. But you can't poke sort of inside it. And I will explain why later on. Okay, so here's how we create it. First of all, we create an actor system. An actor system in Akka is sort of a container in which your actors live. You can have multiple actor systems per JVM if you want to. That's something we've changed from the 1.0 series to 2.0 series. So now you can have multiple actor systems in one JVM if you want to. And there might be reasons for you to do this, but I would suggest when you start with Akka to just use one actor system per JVM. So then you give it a name, my system, for example. The next thing is to actually configure the actor, and we do this by pointing to the greeting actor class and wrapping that in the props. And this props can be used to apply different things onto the actor, outside things that doesn't belong to the actor, but you can apply it onto later. And then we give the actor a name. In this case, it's called greeter. If you don't give the actor a name, it will receive an anonymous name automatically. And in this case, we're using system.actorOff to create it. So normally, if you're, I'll show you later. Maybe I'll explain that later. System actor.off is better. And then you get, here's the interesting part, you get an actor ref back. And in Java environment, we're used to doing new class, and then we get the class reference back, right? In Akka, you never get the actor back, you get an actor ref back. And this basically means that you can, if I would write a method inside my greeting actor called hello, def hello there, I couldn't do greeter.hello to access it. It wouldn't be allowed because it isn't, I'm not looking at greeter actor, I'm looking at the, all I have is the actor ref. And the only thing you can do with an actor ref is sending messages by it. Or you can also create futures, but yeah. So this is sort of the decoupling from your actual actor instance and the code that's creating it. And this also means that you can't poke inside the actor to do stuff. The only thing you can do with it is sending messages. And by doing that, we know that you're communicating with the actor in a safe way. And this is super important. It's sort of this is the reason why we can guarantee scalability. And that you don't have to think about threads or anything. So here's what I talked about a little earlier. At the top level, we have something we call the guardian actor. When you're in the guardian actor, which is on the system level, you remember when we created the system here? Then you're on the guardian level, or you're using the guardian actor to create an actor. So then we write system actor off, and then here we're creating an actor called food. But if we're one level down in the foo instance, when we want to create an actor, then we write context actor on. And so if you're in the context of your own actor, you should write context actor up to create new actors from that one. The context actor up is super fast, so don't feel afraid to create as many actors as you want to from inside your actor. If you're on the top level creating a system actor up, that's not as fast. So we recommend that you sort of create an actor, and then from that actor create a lot of other actors if you're having a lot of actors. So here's what it looks like when we're creating the A actor, and then it goes on from there. You can create how many actors you want to. The cool thing about this, though, is name resolution to find actors is exactly like a file system. So maybe you can guess -foo or /A to get to the next level, B to that one, and so on. Right. And that's also how you can access different actors by just, if you know their names, you can point to them with this file notation. Alright, so we've defined the actor, we've created it. The next step would be to communicate with it. So we're doing that by send. So sending messages. It's asynchronous and non-blocking, which means fire and forget. And this is also a very, very fast thing to do, to send messages. It won't block the thread you're on, so your business code will just send something and then continue with what it's supposed to do, instead of waiting. I mean, in a job environment, we're sort of used to having an HTTP call to the web server. The web server calls the application server, and the application server calls the database. All of a sudden, we're having 3 threads, 2 of them waiting for the third one to finish, and then when the database returns, it sort of releases the threads and returns the reply. Instead of doing this, I mean, this is really, if your database calls takes 1 second, you're blocking 3 threads for 1 second, right? For 1 call. That's not using the hardware the right way. So instead, use asynchronous calls, whether or not it's with Akka or some other framework. If you want to use your hardware, use asynchronous communication. Yeah, everything in Akka is asynchronous and lockless, which means everything happens reactively. An actor is passive until it receives a message. And you can think of this as kinetic energy in your actor system, which basically means you have a lot of potential energy in the system, but it won't do anything. An actor doesn't, take any resources apart from your memory, of course, the RAM, where it lives. But if you don't send a message to an actor, it won't take any other resources from your hardware. And in our environment, we have, luckily we have a machine with 48 cores on it, and running some tests, we came up to plus 50 million messages per second with 100 actors. And that's pretty impressive. Of course, it's not a real test in the sense of these actors aren't doing any business logic, they're just sending messages, right? But it's to prove that it's quite fast. Yeah. I think it's kind of impressive. Okay, so to send a message to this actor called reader we created before, we use this bang operator. This is it's a DSL that we created. Since we're in a Scala environment, we can do cool stuff. So it's a DSL, actor DSL. So basically you can use this notation, or you can write reader .tell and then the message, and that's how you would do it from a Java environment. Then you would have to call the method called tell on the reader, on the actor. And in this case, we're just sending it as greeting with the message ScalaCamp. So the full example would be this. Not a lot of code, send almost 50 million hello messages if we want to. Okay. Yeah. Any questions so far? Okay. So I spoke earlier about this being, what I showed before was just to run it on your local machine. To remote deploy stuff, you can, all you have to do is change the configuration file. When you run your Akka system, you have a configuration file that sort of describes the environment, how it's going to be run. And by changing that, you sort of change the behavior of your system. In this case, we're remote deploying. We want to remote deploy the actor, so we want to deploy this actor on another machine. So we say we want to use the remote actor ref provider instead of the local ref provider. And we say that this is for the greeter. Remember, we gave it the name the greeter, so this would be the name of the actor. And then we define the path. So we have our own protocol, Akka. And then we say what actor system this should be put on or into. And then the host name and the port. Remember, we could run multiple actor systems in one JVM, so therefore we have to point to what actor system we want this actor to be deployed on. So that's it. You don't have to change anything in your code. You wrote it as if it was going to be run on your local laptop, but then you can all of a sudden deploy it into an Amazon EC2 environment easily by just changing the configuration file. You don't have to do any. There's no optimization of your code you can do. Well, maybe if you write, non-optimized business code, I won't give that guarantee. But from the Akka point of view, it looks exactly the same whether or not you would run this on your Android machine or a SIL system.
I have a question here. How to deploy anonymous actor on remote environment?
No, I would suggest you give it a name. Otherwise, it might, randomly be different actors you're deploying. So.
All actors created by greeters will be automatically deployed there. Or we have to...
No, I'm not sure about that actually. I'm not sure about that. So I can look that up afterwards. Yeah, that's a good point.
Remember, you have to define some wildcard.
Yeah, you can use wildcards for doing this. There's this whole language for looking up actors. You can use, when you look up actors, you can use wildcards and stuff like that as well. And the notation of dot to go to the same level as you're on, and then to another. Yeah. Okay, so the next thing I want to show you is how to create routers. Load balancing. A lot of load and a lot of balancing. It's good for that. So, routers, again, we had our greeting actor and it was really popular. It became the coolest service on the web. So we got /dot and we need to, instead of having just one actor, we want to use 5 actors instead. So basically what we do when we create this actor, system actor op, normally it would say context actor op, but never mind. I would recommend say context actor op here instead. All you have to do, instead of doing the props greeting actor as we did before and gave it a name, is say .with router and then tell it what router to use. In this case, it's a round robin router, so it would go through 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. We have a couple of other routers out of the box that you can use, but round robin is probably the most famous. Right, so no code changes again. What if we want to sort of have a adjustable routing functionality? Well, then we just define it with a resizer. So we can say lower bound is 2 and upper bound is 15. So now we sort of we know that we'll always be between 2 and 15. Obviously this is from code, and if you do it in code then you're stuck with it. You have to change the code or recompile. You can do the same thing from the configuration file. So in this case we tell the greeter to use a router round robin, number of instances is 5, Or we can do the same thing with the resourcer. So again, no code changes, which is pretty awesome.
So how to send a message? You send a message to the load balancer, or you send a message to Akka?
So you will call greater, and you don't know if greater is a router or if it's an actor, and there's no way of finding out, and you don't really have to know, which is also a cool thing about Akka. You just send a message, and then basically we want it to be transparent, so it could be a local message or it could be a remote message. You don't know. You just send a message to someone and tell them to do something. In this case, I mean, you would know when you look it up if it's a remote actor or if it's local, right?
So the question here is what for I need this reference to router in that case, because you show us a piece of code, yes, and here we have system.actor and we have this router. So this we shouldn't be aware of that we have such object like router. Yeah?
No, there's what you get back is an actor ref. So the router, the valid router is actually of type actor ref.
Yes, but I don't use it. I don't use it to send a message. I'm still using the greeter.
It's just better name because it should be val greeter.
Yeah, yeah.
And you send messages to the object. Would you?
Yeah, that's true. Yeah, it should probably.
What's the alternative notation to the configuration file? If you configure the configuration file, you don't use the creation in the Scala.
No, you should. I mean, that's what I mean. I just showed you that you can do it from within Scala, but then you have to know beforehand that you want the router, right? So therefore, it's better to do it afterwards with the configuration file, like this. That's definitely something I would tell you to do. Okay, so another cool topic that you can use is become, and it dynamically redefines the actor's behavior, and I'll show you how. It's triggered reactively by a message, of course, because that's the only way we can communicate with actors. And you can think of a become as, in the object-oriented world, as if you change the interface, protocol, and implementation in once, which is something that is tricky to do in Java, but here we can do it. Yeah, that's something I should probably tell you. I mean, in the actor, in the receive method, what you define as expected classes is sort of you can think of that as the API to the actor. It's what can operate on. If you send a message to an actor which isn't defined, then this will be forwarded into something called dead letters. So that message will end up in dead letters, which is another actor on top. And you can listen to messages being sent to the dead letter actor and sort of retrieve information. You can think of it sort of as event sourcing. Yeah, so become. When you send the become message, the actor will then thereafter react differently to the next coming messages. You have this in queue, and you send a message and tell it to become something else, and thereafter it will be totally different to what it was before. And these behaviors can be stacked, so you can push and pop behaviors back and forward if you want to. And why would we want to do this? Yeah. It's one way of adaptively transform an actor into an actor pool or a router, and then you have done it programmatically. So you can send a message saying heavy load, and then it will turn itself into a router. This is probably not something I would recommend the first line. The second line, however, using it as a finite state machine, then it's really good to use the become. Or you can implement graceful degradation if you sort of want to close down parts of your system, saying, okay, you're not supposed to operate anymore on the messages, just forward them to somewhere else or something. Or you can just spawn up an empty generic worker process, and then you can send messages and tell it to become something, and then it will do stuff on the messages it receives. Or use your imagination. And this is very useful once you get used to it. So here's an example of how you could use become. So we define the receive method, and we tell it to call the method expect hello. And expect hello returns the receive. So this is sort of, whenever you send a message to this actor now, then all the messages will end up in the expect hello method there. And if we receive a case or a class called hello with a name in it, then we send back the message hello there name. You see the sender there? Whenever you send a message from an actor to another actor, then sender is something that will be passed on as well. So if actor A sends a message to actor B, then sender here will always be actor A, if you're an actor B, of course. And you don't have to do anything. You just send messages, but the sender actor ref will always be passed on behind the scenes. So therefore, we can just say sender, and then the bang operator, and hello there name. And this will then return the hello there plus name string to whoever sent us this message. If we should, and then the most important line here is context become expect goodbye. So after someone has sent us hello, then we turn into something else. Then we say, okay, you're no longer the expect hello actor, you're now the expect goodbye actor. So, and if we're in the expect hello mode, and someone sends us a goodbye message, then we say, what? Because we're not supposed to operate on that. And the same goes with expect goodbye. If someone says us hello, then not now, we return not now. However, if someone says goodbye, then we just send back see you later, dude, and then we turn back into expect hello. So this is how we can switch between two ways of acting, and so this is a very simple finite state machine, of course. Yeah.
So what can we do if we have routers configured for this app? Because in that case we can't know to which actor the message is dispatched.
Yeah, I don't
change for all actors inside the router.
You have a couple of good questions that we should probably go through after. Yeah, I'm not sure in the routed context. Speaking about routers, that's something you should fall back to once your application, when you've established sort of that you need to use routing. That's why I don't think you should program it into your actual code, rather than have it on the side and then start using routing as sort of the next level of your application. Out of the box, with plain actors, Akka scales really well. So start off by using just plain actors and communicating with plain actors. That's also a recommendation I would make. Before you start thinking, oh, this is going to be popular and Facebook, and yeah. And you had a question as well?
I just wanted to ask how to implement the old-fashioned way, but I understand that in that case we would have some variable, yes? In Akka, and we switch.
You mean in the old...
Yeah, if I wouldn't use this context,
yeah, I mean, in the plain actor, you can also use state, of course. So you can have a variable that you switch, and then when you receive a message, then you can define what method to call based on this variable, true or false, or am I in hello mode, true or false. And then you can call different methods. Yeah, you can do it if you want to as well. But then you don't get this stack, you know, that you can stack behaviors on top and push and pop, which is something that you might want to use. Yes, yeah, that's true. That's very true. Okay, let's talk a little about failure recovery and Java, C Sharp, and so on. For those in the back, the text says here, why we insure women only. It's an insurance company in South Africa. I love this picture. I couldn't imagine four girls lying down and the fifth jumping over with a bike. But for guys, it's perfectly normal. That's why they don't insure. That's why they don't insure or the guys, I guess. Right. So in other languages like Java and C, C#, you're giving a single thread of control, and if this thread blows up, you're basically screwed. So you need to do your own explicit error handling within this thread environment, right? And to make it even worse, there's no way you can propagate these errors between threads. You're sort of in an isolated environment, so if something blows up, there's no way of telling the others that something is wrong. So this boils down to you you have to do defensive programming with exception handling tangled with your business logic. I mean, yeah, I'm sure you're well aware of this. And it's scattered all over the code base. So we think we can do much better than this. Instead, just let it crash. And our website is letitcrash.com.
Oh, she's definitely text.
Nice. So, okay, if we let stuff crash, this basically means we need to supervise things, right? Otherwise it would just blow up and no one would know. And supervise in the act environment basically means that you manage other actors' failures. If you create an actor in Akka, then you're automatically supervising it. Which basically means that I'm supervising all my children if I'm an actor and I create actors. So if something goes wrong, if an actor blows up, a notification would be sent to me as my supervisor, and then I can decide what to do, how to react upon it. And this sort of separates the business logic from the error handling, which is exactly what we wanted to achieve. You can think of it as a error kernel, an onion like this, where you have the most important thing in the middle, and then you have layers outside, protecting the most important thing. I don't know if the most important thing in an onion is the centerpiece, but you get the picture. So here's what it looked like. If you're still thinking about this layers, then the middle part of the onion is the red circles there. Okay, so something blows up, it's supervised, so we send a message up to its parent, and the parent decides to recreate it. We can also, so that's 1 for 1, it's called 1 for 1. We can also do all for 1, which basically means that if one of the actors created, one of my children dies, then I will recreate all of them. It's called bad parenting as well. Bad parenting and patterns. Yeah. So don't use that. And we can also decide to escalate. So if my child blows up, I will also blow up and call my mom. Who then decides to, let's not forget that. Yeah, but as you can see, you can escalate errors and restart all of them, or all the actors with just one. Finally, if everything goes haywire, so we can decide to start up the actors to another node. I mean, if something is really bad on the machine or something, we can just say, okay, from now on, do your stuff on this machine instead. Yeah, as I said before, every single actor has a default supervision strategy. It's normally okay to use it out of the box, which basically means that you don't have to do anything, but if you want to, you can override it. So here's what that would look like. We override the supervisor strategy. In this case, we also give it a couple of properties. It says max number of retries 10 within the time range of 1 minute. So if this happens more than 10 times within that minute, the actor will be stopped. But then we can define how to react on different things. Like if we get an arithmetic exception in this case, we just resume. Resume in this case basically means that just continue with what you were doing. So I have my actor, and it returns an arithmetic exception. Probably it received the value 0 and tried to divide with that. And that's perfectly fine. We can catch that over here if we want to, if we didn't have clever code to realize that before. And we could just say, okay, resume with the next message. Or if we get a null pointer exception, then maybe we need to restart the instance. So then we recreate it. I mean, resume will still keep the state internally in the actor, but restart will recreate a new instance for us, and it will lose the state. Maybe it was the internal state that made the null pointer exception happen. So we decide to recreate it instead and start up from scratch. Or if we receive another exception, we can just say, I don't know what to do with this. Let's call my parent and see if they can figure out what to do with it. And yeah, so basically that's all you have to do.
What do you actually do when the max retries number is?
The actor would be stopped.
Will be stopped.
Yeah.
And the parent will be notified.
The parent would be notified, yeah. But then you have to, you do notification by watching your children instead. So you have to watch the child if you want to know if it dies.
Twoje pytanie. Jeżeli maszyna zdechnie, to musi być świadom tego, że może zdechnąć.
You get the feeling. Okay. Also, an interesting thing here is the for. You see, instead of doing worker bang n, we do a forward, and forward basically means if actor A sends a message to actor B, and actor B does a forward to actor C, then actor C will have a reference to actor A. And this is super efficient if you have a lot of layers, actors that are communicating in one way like this, and you want the final one to return to the first caller, then you will just forward the sender reference, and so the last actor can, instead of sending messages back through the whole chain, you can call directly to the first one. So forward is a really nice feature. Yeah, we also have lifecycle hooks, so you can hook into, in this case, pre-restart and post-restart. Pre-restart is done on the old instance before it's stopped, and post-restart is done on the new instance before it starts. So you can, if you have like a database connection or something that you want to clean up, then you do that in pre-restart, and then post-restart you sort of create new ones. And we have other lifecycle methods as well. Right, so that was everything about Akka. Now I'm going to show you a new feature, Akka Camel.
Who is supervising the system? The master?
The Guardian.
Yeah.
The Guardian is supervising everything.
Who is supervising the Guardian?
Yeah, that's a good question. Yeah, who's supervising the supervisor? Yeah. No one knows. No, I mean, if something goes wrong there, it would just, the whole system would go haywire. So basically that's it.
I would like to ask about your slide. I mean,
This one?
no, the next one.
No, the next one? Okay. Hold on, all these animations out there. No.
About this forwards, yeah. I mean, you said that I have a reference, let's say the beginner of this action, yes? This is something which is exposed as a sender, or this is something which is exposed somehow in different way.
So in this case, this is in the actor. So you're in the actor, and this is where you write this code.
No, I mean,
About
when
the
we
sender,
have
about the forward in the sender.
Ah, the forwarding, okay. Yeah, so what was the question about forwarding?
okay, so when I'm using this forward feature,
Yeah.
yes, and someone wants to handle this, yes, and send back the message to the originator of this message,
Yeah.
and it is using the sender, yes?
Yeah, so sender will then become the forwarded reference.
Yeah.
So as a receiver of a message, you never know who you're returning a message to.
Yeah.
by using sender. But if I mean, as a developer, in this case, say I have 5 actors that I call in one sort of sequence, and then the final one is going to communicate the result back to the first one. Then I don't want to send messages back all the way, right, to get to the first one. It's much better to call.
Some kind of optimization.
Yeah, it's some kind of optimization, yeah. But it would be normal to use this sort of if you have a REST API and then you have Akka in between. The REST API also, you have actors there, they receive the message or the request, and then they forward this to some business logic, and then you have a database actor retrieving data. Then the database actor can return it directly to the sort of HTTP actor if you want to.
I have one question on this thing. So let's say one after crash, we decide that state is invalid and we want to do a copy recovery starting the actor. And we have some kind of status on the actor, and we know that part of the state is correct, and we want to somehow serialize it because it's important for us and we don't want to use it during the restart. Can I, for example, in this pre-restart send message to the actor, or state of the actor is invalid and I cannot do anything in the actor system?
No, you can do stuff with the state you have and store it or forward it and send it from there and clean up or fail back or whatever you want to.
Send message to yourself in the.
Yeah, you can send a message to yourself as well. Yeah. But you don't know. I mean, if you have multiple of messages already in queue, it will be the last one, right? So you don't know it for sure. Yeah. Because in Akka, you can't bypass that. You only have one in queue or one, where you place messages. So and all the messages before that message will be processed. So you have to do it other ways. But yeah, there are ways for doing that. Right. So I'm just going to show you how to do. I don't know if you're familiar with Camel. It's quite a big library from Typesafe. That you can use to communicate with other things. I mean, normally you have more than your actor system and you want to communicate with the outer world. Unless you're calculating pi or something, but most of the time you want to communicate. So here's how you would use what you have to do to make your actor sort of the consumer actor. You can point it to the endpoint URI, and then you expect a camel message in your receive method here. And you can, of course, this endpoint can be a file, or it can also be something else. So that's how you consume messages in camel. Quite easy. Or you can produce messages by, in this case, listening to a JMS queue, and then send. You just create this as a normal actor. The only thing is you also mix in the producer with one way here, but from there on it's exactly the same. Now we're creating an anonymous actor, but that doesn't really matter. And then we send some sort of it's some XML to it. Right. I'm also going to touch on the cluster subject. Akka 2.1 was released recently, and we've added clustering into it. It's an experimental module, but I'm going to go through some of the topics. So basically, we have a gossip-based cluster membership. You have a lot of nodes or actor systems deployed on different JVMs, and when they become part of the cluster, they will send gossip messages to each other. We also have implemented an accrual failure detector, which basically means that the failure detection is detached from the application itself, and each node will gossip about the states, what it believes the state of the other nodes are. So each node will communicate. We also implemented a cluster death watch and cluster aware routers as well. So with the gossiping protocol, it's used for cluster membership. You can configure data. We also did have leader determination built into it. So we have a leader in the future upcoming versions, we'll also partition data and use it as a naming service. So to enable clustering again, configuration base. I'm not going to go through the exact details here. You can look at our website for how to do it. But basically, we just instead of using the local Akka ref, we're using the cluster Akka ref provided. And here's how you would define a clustered router. In this case, we're saying that it's a consistent hashing router with 15 instances. Max number of instances per node is 3, and allow local routines to be on. So easy as that. Right, and so that's basically what we have enabled in 2.1 in the current version. In the next version called Rollins.
What's the main purpose of the cluster?
Yeah, that's a good question. You would have to ask anyone who's using a cluster. No, I mean, cluster. Yeah, so hopefully that will become clear when I'm done with the slides. But yeah, if you have actors on multiple nodes and one node dies, then you have actors on other nodes, right? Yeah, so it's sort of the normal CAP theorem, yeah. Yeah, so Coltrane, the current version of the clustering has one actor tree per node. Actor tree being all the actors you created in this actor system. Rollins, however, will work a little different, where you can define to map different parts of this tree onto different nodes. I will show you in this case. Yeah, so in the next coming versions, we can do this. So define the actor tree and say, okay, the load is a bit heavy, now we separate this into different machines. The cool thing about this, though, is as a user of the Akka ref, you don't know really that it's being rerouted to somewhere else. You think it's local, or you think you don't know it, you just have the Akka ref and you can use it to communicate. You send a message, basically, and then you don't know where the message will end up and where the actor is. So, yeah, you know that the message will end up for that actor, of course. You don't know where the actor is. And this basically means that we can now move actors around in the environment, and you can think of it as we can look at the stats of how your machine is doing, and then if it's under heavy load, then we can redirect some actors and move them to another node. Yeah, Akka migration, Akka replication, automatic cluster partitioning based on runtime metrics, and node failover. So the node failover, the initial version will be only for stateless actors. So if you have state in your actor, then the state will disappear. But later we will also use event sourcing for enabling this for stateful actors. So if an actor dies, we can just recreate it into the state it was on another machine. And fault tolerance and distribution, I guess, is the answer. You can read more about it there. I will share these slides later on. Yeah, we have much more in Akka. Someone mentioned FSM, but we also have a test kit for how to test actor systems and a lot of other cool things. So Akka.io is the website where you can find information. Our blog, where we blog a lot about Akka and other topics, is letitcrash.com, and of course Typesafe.com, where you can find more information about Akka or Play or Typesafe in general. So that was part one, the Akka part. So now the next part would be the case studies. So I'm going to just briefly talk a little about Royal Netherlands, Mauritius and Guild. I'm sure you're aware of both of these now. So the main function of RNN is to combat illegal resident smuggling, trafficking, and cross-border crimes. It's in Holland. So they decided to build a new system for this, and basically what they do is they collect data for traffic profiling. You can think of this as cameras constantly watching all the cars passing into Holland. or I guess airports where people come into the country. So I mean, it's a lot of information that's being processed in runtime, and they need to be able to respond to quick alerts. So basically, it needs to be real-time system, because they're selecting cars to stop. So if someone drives past one of the cameras, then an alert will be generated, and they sort of drive up to that car and stop it. And, yeah, try to find out what's going on. And they decided to use Akka because, first of all, ease of use, but also it leverages the existing Java investments. I mean, most of us are coming from a Java environment, so not being able to use that environment would sort of be a very costly investment. So, of course, you can use your existing Java environments from Scala or from Akka. And finally, to be able to build a system that's scalable and performant under heavy load was one of the main things that made them choose Akka. It's been in production since August 2012, and there's a reference there on our website where you can read more about it. So the next thing is Guild. And Guild is a really cool company. They do online shopping for top designer labels. And a lot of websites do that. But they've sort of incorporated or come up with two cool concepts. One being the so-called flash sales. They have a flash sale every day between 12 and 12:10. So they sell off a lot of things. And it's really cheap to buy these designer labels, but just between that time. And then they have sort of normal price later on, which maybe is cheaper than your average store, but still not as cheap as between 12 and 12:10. Of course, you can imagine that this attracts a lot of traffic. Everyone's refreshing or sort of sitting in front of the website trying to buy these cheap clothes. So that's a cool feature. The other one is being Guild Live. Guild Live is a web page where you go into and then you see what other people are buying. So you sort of yeah, I can go to the next one. They're using WebSockets to push data to you. So you can think of it sort of as a movie when people are buying stuff, and someone bought this jacket, and then now someone bought these shoes. So you can just sit there and see if you find something cool. You can click on it and find it. So this has attracted a lot of traffic to the website. Those two features. They started out as a Ruby on Rails shop. When that didn't scale, they turned into Java for some parts, but they finally made a transition to being a Scala. I don't know if it sounds sense, but they're using a lot of Scala at the moment. Yeah, they had scalability issues with Ruby on Rails, but yeah. So they decided to use Play Framework because it's a modern web technology stack. WebSockets being one of the things we're using it. We're using parts of these cool features for the console as well. And they're using the whole stack, the whole Typesafe stack, so they're using Akka as well. And their chief architect says Akka is key to handling traffic. Okay, so that was the case studies. 5 minutes. Well, you can, as I said, you can read more about it on the website. So now, finally, the last 22 minutes, minus a couple of minutes for questions, I guess. I'm going to go through the Typesafe console. So I told you before how to build Akka applications. I mean, whether or not you're using Scala or Java, it's still going to be compiled down to Java bytecode and run in a JVM environment, right? But using the old-fashioned tools for monitoring will only give you stats about the heap and CPU and stuff. You can't really do the normal things you would do with New Relic or another monitoring tools. So therefore, we provide you with the Typesafe console to actually get statistics that tells you something about how your active system is doing. So it monitors Akka applications at the moment. We're also going to add Play applications to this during this year. So you will be able to monitor both your Akka and your Play applications. We believe in dogfooding, so it's implemented in Scala Akka Play. It's Scala 2.9.2, Akka 2.0.4, for 3 and play to 0. And this comes as a part of the Typesafe subscription, but with the next release of the console, we're also going to give it out for free for all developers. So you as a developer can download this and use it for free in development environment. Then once you decide to go into production environment, then you of course have to pay for it, but it's free for developers.
So how much does it cost?
Oh yeah, call my sales guy. I don't know. It's depending on your environment, so how many machines you're using and so on. Yeah, I think it's negotiable. But I'm not a sales guy. You know, are you filming this? Okay. Sort of a lot of other things from the time. Yeah.
You said you're not a sales guy.
Can't you tell? I try to sort of do my best. Yeah. So the overall aim with the Typesafe console has been that it should always be possible to have it running in your production environment. I mean, most of the times when you run into problems, it's too late to turn a monitoring tool on. So therefore, we want this to be on all the time and collect data, and then you can go back to exactly the point before things started going haywire and say what's happened, how did my system look at this point in time, and then you can forward and go forward and see how your system is, what's wrong in your system. Okay, so here's the sort of overview of the architecture. You have your monitor application on the left-hand side. Instead of using the normal Akka jar as you would if you're not using the Typesafe console, then you use an instrumented Akka jar file. It used to be compile time weaving, but we're using load time weaving now, which basically means that we look at the Akka jar when you start your system up, and then we create a specialized version of it. We're using aspect database. I don't know how many are aware of aspect-oriented programming or part of it. Yeah, good. So that's what we use basically. So we have point cuts in the Akka code. I mean, we're the experts in Akka, right? So we know what's going on in the framework. So we can pinpoint those points and then create trace events for everything that's going on in your system. And these trace events are then stored into MongoDB. Then we have an analyzer running it on another machine, and this analyzer reads the trace events and creates statistics based on the trace events. And these statistics are being stored in both, in 2 dimensions. You can think of it as both on the data side, but also on the time side. So we pre-calculate all the data. All the questions that you can then query MongoDB with are already pre-calculated. So all the data is already there, which makes the query part really easy to run, right? It's just a read basically from MongoDB. It doesn't load MongoDB. So the heavy lifting is done in the analyze part. And then finally we have the actual play application, which is called the console, which is a bit weird when the whole thing is called the Typesafe console, but yeah, that's the way it is. And we have the GUI on the front-end side. So basically, the play application just retrieves data from the query, which is the REST API. And this is where you would, if you don't want to use the console, you can still use the sort of mechanism to retrieve data, or create data and retrieve it from your own monitoring system via the query REST API. So you would just call the query REST API and retrieve data and feed that into your own monitoring system if you want to. Yeah. As I said, we use load time weaving. We store the data in thread local. We batch store into a socket, or via a socket into an offline storage. So we want, as I said before, we want it to be the footprint or the performance overhead to minimize that, right? So this is why, so we use thread local, we store a couple of trace events, and then we batch store it off to somewhere else via a socket. And then we don't really care how slow the storing mechanism, if it's very, very loaded on that side, it doesn't affect your application. Tracing at the moment works for within one actor system or between actor systems in the same JVM, but also between different remote actor systems. So if you have multiple nodes, we can trace a message being sent from one node to another in the back, no problem. Basically, we can trace all the operations that exist in Akka. And no other tool can brag about this. It's available for Akka 1.3, 2.0x, and soon for 2.1, which is the latest version of Akka. Here's an example of what a trace event looks like. It's just parts of it, but everything that's going on in the Akka system, we create these trace events. So in this case, I mean, this bin data is how Mongo stores unique IDs. So you can think of that as unique ID. So all the trace events have a unique ID. And then we have an annotation. In this case, it's a type received, and then you can see that it's actor A that received something. So this means that a message has been sent to actor A, and we received it. And the trace here is the overall trace context. That's the unique ID that follows the flow through the system. We have a reference to the parent who sent us this, and then some other statistics like what time it was, on what node and actor system. So this is what it looks like. I told you we use the socket. So your monitored application will then communicate to a socket, via socket to this collector part functionality. In the collector, you can define that if you want to have it stored directly into MongoDB, or if you're in a cloud environment, you can use an HTTP storing mechanism, or you can use Flume, which is a distributed log system for heavy log, developed by, I don't know if it's Twitter. I think it's LinkedIn. Anyway, it's open source, and it's used to retrieve log files. If you have 100 machines, retrieve those log files into one place. And we can use that for if you have multiple, nodes creating data, we can use Flume for that. Or you can use remote app. Everything's going to end up in MongoDB eventually, though. We also provide a small trace API in which you can create your paths if you want to. If you have a certain part of the code that you want to collect data for only that part, then you would use this mark start in your code and then give it a name and then mark end where it stops. So, for example, the checkout of guild, for example, if it's heavy load, they want to create statistics for just the checkout part when people are buying stuff. It's also possible to collect application-specific data, and you use that by using sort of a grouping ID, the login there, and then user ID 1, for example, in this case. And by doing this, we could, for all the logins into the system, we could use the group login and then the unique user IDs. And then we can get statistics on the console side for this, or look at how many times people have logged on to the system. The deployment is fully text-based, which makes the DevOps really happy. Of course, in the simple setup, your application would run on one JVM, the query and analyze modules would run on another, and then the console on the third, and one MongoDB instance. That would be the normal setup. But you can also, you can run your applications on how many nodes you want to, or how many JVMs you want to, and then you can sort of divide these analyzers. There are 15 analyzers for different statistics, and you can split those up into different JVMs as well. The query is not very machine intense, so that's only one JVM is needed, and the console would be one as well. The cool thing is you can also use different MongoDB instances, one for the actual data storing and one where you store the statistics. So the query would use this, analyzer would use both, one for retrieving data and then writing back to the statistics instance. But this is something you can do when you decide to set it up. Okay, so a quick demo, what it looks like. First of all, I'm going to start off. I'm going to run this locally. And hopefully it will work. Okay, so the normal login side, you can, here you can see that we have given it a name. I don't know if this is readable in the back, but we've given it a name and then we pointed to a URI endpoint. And the URI endpoint is where the query REST API runs. So let's log into it. So here's the, yeah, that didn't look too good. It's
You
the,
can turn off the lights.
yeah.
Oh,
Okay. Yeah, that's much better.
trzymam się do kamery.
As you can see, stuff is loading in the console at the moment, and so basically what happens is, as I said, we're using modern web technology. So we're pushing the console. The client makes an initial request and says this is the data I want, and then we push the individual pieces out from the server to the client. So right now there's no more requests going on from the client to the server. It's just server-side events being pushed from the server out to the client. So here we have the landing page, and the system overview is on the right-hand side, where we can sort of get information about the timing interval here. Right now it's 10 minutes. So we're looking at 10 minutes worth of data, and you can see all the graphs here are to 10 minutes, right? And we can tell the number of nodes in the whole system. We have one actor system, and we have in total 11 actors and so on. And of course the throughput, you can see the throughput here, maximum time in mailbox and other things. On the left hand side, you can see the nodes. So right now we have 2 nodes. There are a couple of errors in this node, which is indicated by this red ring here. So we can click on that and see what errors there are. So error logging from actor E. This is demo, right? So we create a couple of errors on a continuous basis. And yeah, we can also see the trace tree from this. And as you can see, data is being pushed out. Whenever there's a new error, it will end up here. Yeah, all the graphs are expandable into larger graphs. And it's also possible to use the mouse like this to get the value and point in time. So I want to find out exactly. Here it was 55.76 messages per second, and what time. And we also have a lot of more information on the node side of things. You can see the CPU, for example, we gather data like that. Of course, heap, yeah. All these graphs, you can also change. There are a couple of graphs available, so if we want to see the number of threads instead, we will get that graph. And the same goes for the info boxes, so you can change the info boxes to something else here. Yeah. Okay, so that's on the node side of things. If you have many nodes, you can minimize them to get a better overview. In this case, we only have 2, so we can use the sort of normal, but then you can also maximize all of them if you want to. It's also possible to reorder these based on, for example, uptime. You can see the swap because node 2 started before node 1, or errors or whatever. Yeah, so from each, you can see here, this node, node 1, it has one actor system, so we can click on it and have a look at what the actor system looks like. Get some stats from that, mean mailbox size, for example, or max time in mailbox, also the latency for just this actor system, all the actors it has in it. The same goes for the dispatchers. So you get information about how the dispatcher is doing, number of threads and stuff. And finally, you can click down to the actors. And the actors, oh, sorry. So the actors, you remember I told you about the sort of file structure. Here you can see it's represented as a tree. So actor B has created actor C. Actor C is a child of actor B. And it's represented like this. So this would be sort of the statical view of your system. Perhaps a better view is the table view, which is more the more dynamic side of things, where you can see they're sorted in ways. So in this case, we're sorting it in max time in mailbox, but if we want to sort on processed messages, we could easily see that that's actor A. of course, we can click on actor right here and get more specific stats from just this actor, like the mailbox wait time, which could be interesting. It's not that much here. The maximum was like 300 or something. Microseconds, mind you, so that's not too much. Yeah, I think that's about it time-wise. But we're continuously developing. We're also developing right now a sort of alert center where you can create set up rules for when alerts should be created and how to handle those alerts. And, yeah. As I said, this will be free for developers in the next release, which is due to happen end of March, I would guess. So I guess that's it for me.
Okay.
Yeah. So questions.
Do you know anything about class or how it is replacing if someone knows how the old-fashioned actors in Scala?
All actors were moved to the separate jar.
Yeah.
If you want to use them in 2.10, you have to include the separate jar. There are no actors in the Scala jar now. The main method is to use actors.
This is easy. This is just for. Okay, so I have to change something probably.
And there are migration guide, automatic migration from the Scala actors to the Akka actors, but I didn't use it, so I don't know.
No, I would definitely recommend to stop using the Scala actors because that's sort of deprecated and it's being replaced with Akka actors because of a lot of things. One being Akka is a bit more correct. Yeah, yeah. Yeah. Sure. No. Yeah, but if you're from here on forward, use Akka instead if you're building something new.
Let's say some lightweight library for this Akka stuff because let's say I don't need all of these remote stuff because I don't want to have a big libraries and probably I don't know how big.
It's not big.
It's not big.
No. It's very small, so you don't have to think about that.
Okay.
Yeah.
I don't believe it because
Of course you don't. There are no external dependencies.
okay. There's a lot of tries in Java work about this ESP stuff.
Yeah. ESP and Akka should not be mentioned in the same room.
Since I'm here, I mean that some ideas are pretty similar there and here. You have a cube, you have some publishers.
Yeah, but if you work with an ESP, then yeah, I have, and it's nowhere close. Yeah, this is very lightweight. I mean, I don't know if you, yeah, I can show you here. This is when I start up the whole console, which is a lot of stuff being loaded. And of course, SPC, so that's it. It took like 5 seconds and I start up, I don't know how many lines of code. If you would have done this with WebSphere, the normal version, we could have the coffee and then come back, right? So Akka is super fast, even to start up. I mean, so you can stop and start as much as you want to when you develop, and it's no pain at all. And that's one thing that I love about it.
If I want to install a new version of application of better new code, yes, the hack for some actor, I want to so I must stop the whole system and restart the
yeah, you have new code, yeah. But you can, I mean, yeah.
So I can't to add new actors with the new process and
yeah.
to turn off the old.
Właśnie przeładowanie systemu może być problematyczne.
Yeah, good. Yeah.
And it's modularized. I found it's modularized. There are
Yeah.
6 or 7 separate jars.
Yeah.
You don't have to include everything.
So if you can live with 1 meg, then that's fine.
Okay, this is amazing, yeah, because people are struggling with it for many years, and you have a new product, yes, and you say, we are right. guys, yes, you produce crap. Now it's our, let's say, our time. Yes, that means, and it is whether it was done by also some, let's say, people who know how to implement it.
Yeah. I mean, we don't have sort of any rules to live by apart from how the actor model is. So we started from that. Rather, I mean, if you're working for, I won't mention any companies, but I mean, big companies, like, yeah, there you have to use certain framework and certain library to build stuff. We didn't have that, so we could start from scratch. And yeah, so it's lightweight and it's fast.
This console collects lots of data. Does it have an impact on system performance?
Yes, it has an impact, but it's that impact is sort of linear to what you do in your business logic. If, for example, if we were to run the console on this 50 million messages per second, it wouldn't be 50 million messages anymore, right? Because we would instrument a lot of information. But normally in your actor, you're doing something, you have some business logic, and the longer it takes to run that business logic, the less impact the console, overall impact of the console will be, right? So it's sort of in proportion to what your business logic is doing. But as I said initially, we want you to have the console enabled in production at all times. So we're constantly working on minimizing the performance impact. But yes, there is an impact. Yeah.
Can you customize the data? I mean, what we are gathering from endpoints.
With the trace API, yes. The methods I showed you, it's possible to send in data into the console. But apart from that, no. Yeah.
Do we have any form of casting of messages? For example, when we have keynote, we will send a message to the second node. It will be stored in some queue, I believe. For example, at this moment, this second node goes down, and it goes up with a newer version. And the newer version requires a newer version of this message that was sent.
I think we should take that question offline later on. Yeah, there are patterns for doing this. Yes, but yes. Okay. Okay. Yeah. If it's allowed.
Nic nie chcę tego zrobić inaczej. Już stagamy. To jest cały problem wymiany kodu, który de facto też jest albo byłeś na ostatnim? Over the top bit?
Yeah, we do a lot of more things in the background for the top level or for the actors being created from the top level. Yeah.
Są problemy ludzi, którzy trochę nie opisali kodu, Ty jesteś skrzywiony olimpiadami. Jesteś.
Yeah. We would still have to do stuff
tak, nie chodzi o to, że nie powiedz mi, że pisanie kodu z tego nie spowodowało zmiany drobną z tego.
Right, that's it. Thanks, guys.
Dzięki. Zapraszam teraz jeszcze na krótką przerwę, ale po następnej prezentacji już nie będziemy robić żadnej przerwy. Są dwie krótkie prezentacje w sumie i to wszystko.